Welcome for today's live session, fifth week 5 live session for Advanced Research Trends in Smart Grid Technology. My name is Meena and I am currently doing PhD in Electrical Engineering Department at IIT. So let us begin with today's session then. So we will follow this agenda for today's session. First, we will briefly discuss the overview of week 5, and then we will discuss some questions as well as related topics, and then you can ask your doubts. In between also you can ask your doubts. So just to remind you that the deadline for assignment 6 is March 8th and for assignment 7 is 15th March. Also, you can find the recordings of the live session on this URL. This PPT will be shared with you. In the problem solving tab in the portal, you can see the link for the Google Drive. There you will see all the links for recording as well as presentations. So let us move to overview of week 5. So in week 5 we discussed two main topics. One was the anti-islanding detection techniques and smart grid protection. The introduction to smart grid protection, where we discussed different protection issues because of penetration of distributed energy resources. Let us move to the first one. So first one was islanding detection techniques. So in that first we started with microgrid. Then we saw what are the advantages of microgrid. Then we discussed the necessity of islanding detection. And then we discussed different types of islanding detection techniques. We also discussed about the non-detection zone. So microgrid is a self-sustained system and it can operate in 3 modes. One is grid connected mode, then islanded mode, and third one is a transition to island and reconnection mode. So both the transition from grid connected mode to island mode is one transition, and second transition is from the islanded mode to the grid connected mode. So these two are the transitions. So this first transition, second transition. So both are correct mentioned here. So this is transition to island. So this is the first one, and reconnection mode. This is the second transition. So, what do you recall? What are the necessities for islanding detection? Why do we need to go for islanding detection? So any of you do you remember? Yes.
To get isolated from fault, remains healthy, that section.
Yes, that is one point. That is a good point. So if there is a fault on the grid side, we want to isolate the microgrid so that the fault current is not fed into the microgrid and the equipments inside the microgrid is not damaged. So that is a good point. Let us discuss islanding. So islanding can be both intentional and unintentional. And when we talk about these islanding detection techniques, then we are focusing on this unintentional. Because intentional, we know we are doing it. So this is already planned, and or if not planned, then as per the contingency, we already have a systematic plan to do the systematic separation of main grid to avoid major breakdowns. So these can be due to several possible scenarios, like to overcome blackout and cascading failures. For system maintenance also we do this. Then load curtailment, this is the most frequently used. Whenever the generation is much less than the load, then we have to curtail the load in order to maintain the frequency. Then temporary faults. So all these are intentional islanding, and we have a control over these. But these are the scenarios where we need to go for unintentional islanding. So these are without any planning, and we don't have any prior information from either the main utility or from the DERs. So this can be due to faults at the main grid, then system failure on the grid side. For example, blackout. If blackout happens, to prevent this we use this intentional, but even after employing those preventive measures, if blackout happens, then this is called, there is a system failure on grid side and we have to go, then it is unintentional islanding. And it may be also due to human errors and natural disasters. So we are focusing on this one, unintentional islanding detection techniques. This is our main focus in this course. So these are the islanding detection techniques that we have gone through in the lectures, the first 3 lectures. So the islanding detection techniques can be broadly classified into passive, active, hybrid and communication types. Then passive can be of 3 types. One are the conventional, then second signal processing based, and then the new ones are these AI techniques, also signal processing. Both these are newer. These are the conventional one. Then in active we have 2, current injection based and positive feedback based. Then hybrid, which involves the combination of both active and passive. Then finally we have this communication. This is also called remote. These remote techniques, because here we get signals from a remote distance. So this is based on remote operations. So in each of these we have different methods. Rate of change of frequency, rate of change of power, rate of change of angle, then under voltage over voltage relay, under frequency over frequency, power quality, impedance matching, impedance monitoring, voltage imbalance. So we have seen in lecture this impedance monitoring, power quality monitoring, rate of change of frequency and rate of change of this power angle. These 4 we have seen in the lectures. This voltage imbalance also we have gone through in the hybrid one. In hybrid we saw one technique where passive technique was this voltage imbalance. So these are the most widely used conventional methods because they are easy, their implementation is easy first, then they are economical, and there is no power quality issue. But the problem is large non-detection zone. When the active power mismatch is 0, then these techniques fail to detect islanding. So they need a minimum threshold for the successful operation. And we have this signal processing based, where we have S transform, wavelet transform, or energy based. So we saw one method of this energy based for this one. So energy of phase energy of this rate of change of phase angle. This we saw in the lecture. So benefit of these signal processing based techniques is that the non-detection zone is lower than the above conventional one. Also here also we don't have any power quality issues, but the problem is high computational requirement. And in AI techniques, these are the new latest, we can say latest addition, where we use, these are all data driven. So for them we need data, lot of data. So here also the difficulty is they have advantage over the first two, but the problem is difficulty in practical implementation. Then in active we have this current injection based. So this also we saw negative sequence, superimpose negative D-axis harmonic current injection method we have seen. So here the advantage is that it has the non-detection zone is less in comparison to the passive techniques. But the problem is power quality issues, because here we are injecting harmonics, we are injecting some disturbance, and which leads to power quality degradation. Similarly, in the this positive feedback based techniques, this is also good with respect to the non-detection zone, but the problem is that some techniques like AFD, active frequency drift, they have power quality issues, and the other problem with all the techniques is they drive the generator into the unstable mode. That is the biggest disadvantage. So, can anyone tell why do we go for hybrid techniques? Because in active we have negligible non-detection zone, and also in positive feedback based the power quality issues are also very less. In some techniques there are no power quality issues. So why are we going for hybrid techniques? Any guess? Any idea?
It is mixture of two. It will have some advantage of both.
Okay, so what
It is
is?
like guess.
Yeah,
Guess.
that is true. So
Yeah.
what is that advantage?
Not very much sure. Your touch plan.
So thank you for responding. So you made a good try. So what we can say, the advantages of passive technologies is that they are simple in implementation. If we use the conventional techniques, these are simple in implementation and also economical. So their advantage we can exploit. In active, what is the advantage? But the passive and disadvantage of large NDZ. Active has advantage of negligible NDZ. So we can exploit these two. And in hybrid, in active what we do, we continuously inject these disturbances. So continuously injection will lead to more power quality degradation. But in hybrid we will not do continuous injection. We will first of all use the passive one. If it is not able to detect, then we go for the active one. Then only we will inject. So continuous injection of disturbance is not there, as a result of which the power quality degradation is much less. So that is why there is a significant reduction in the power quality issue. In subsequent slide we will see a block diagram for all these, and then there is a better detection capability than conventional because of this anti-Z issue. It is not there. It is very less. And finally the communication one, this is the fastest method, and also very negligible, or we can say almost in some technology there is no NDZ. There are no power quality issues also, but the problem is here high cost. The communication infrastructure requires a lot. It's expensive. So let us see the first technique. So this is the passive technique. So here we will do what we do, that we just on the PCC. So here we have grid, and this is the PCC. And here if we have a TER. So on the PCC we will measure different parameters based upon the technique. If it is a voltage unbalanced based technique, then we will measure the voltages, and we will do the V2 by V1, the negative sequence voltage and positive sequence voltage. So we will measure the the appropriate signals, analyze them, and then we will check their value with respect to a threshold, which is a predefined value which we have to decide. So if this value of parameter is greater than threshold, then there is an islanding. If it is not greater than threshold, then there is no islanding. So here it should be disconnect DG. So but here in this problem, in this passive techniques, the problem is how to determine the threshold, how much should be the threshold. So designing of threshold is a challenge here. Then another problem is that we have discussed already, that for zero active power mismatch it doesn't work. There will not be any change. So it fails to distinguish between islanding and non-islanding situations. Then the rate of change of frequency performance is also affected by load type and the generator inertia constant, because these things determine the frequency. So when they change, so frequency will also change. It will be affected. And the threshold is based upon the frequency, the nominal frequency that we have decided. But if these parameters will change, load type and generation inertia constant, then the threshold will also have to change. So any doubt up to this point? No doubts, and let us move to the next one. So next is the active techniques. So in active techniques, the main difference here is this injection of disturbances. So we will inject some disturbance at the PCC, and then we will measure the signal, and then the same procedure is followed. And because of this injection of perturbation, there is degradation of the power quality. The next is this hybrid techniques. So here it is a combination of the passive as well as active. We start here, we measure the signal at PCC, we check whether it is greater than threshold. If yes, then islanding. If no, then we have to inject. So here you can see the injection is not continuous. So the injection is only at specified intervals. So because of this, we significantly reduce the power quality issues. Then the next one is this communication based. This should be started. So we start the algorithm here. So there are two. Suppose this is the grid side, and here we have different DGs. Suppose this is DG1, DG2, So here we will have one transmitter on utility side, and here we will have some receivers. So the transmitter will send the signals, and the receiver will at DG side will receive. So if the signal is received, then there is no islanding scenario. But if the signal is not received, then there is an islanding scenario. So then we have to stop and disconnect the DG. So these technologies, so there can be different, like PLCC can be used, then SCADA can be used, PMU based can also be used, but all these two are very costly. So the drawback of these technology is the cost. Otherwise, this technique is good. So then after these islanding detection techniques, we discuss protection issues in smart grid. So we discuss major the 4 different types of protection issues. One is dynamics in level of fault current, bi-directional fault current, false stripping, and blinding of detection. So we'll discuss them after discussing the questions. We will see them. Do you have any doubt in these 4 protection issues?
Please explain some more on false stripping.
Okay. Let us discuss this. So let us start with this. First is dynamics in level of fault current. So this first scenario shows that this microgrid is connected to it. So this first one is a grid connected mode, figure A, and this one is the islanded mode. So when there is a fault here, let's call it F, fault F. So when there is a fault here, grid connected mode, the main grid is also feeding in all these 2 generators. All the 3, there are 3 sources of current. So 3 source current are feeding this fault current. But in islanded mode, only these 2 sources are feeding the fault current. And so if we design the relay setting, if relay is set as per this current, then this setting will not work here. Because what happens here, the fault current, if it is based upon the type of distributed generation, the fault current is limited. Here it is only 2 per unit, here it is 5 to 8 per unit. So this current will depend upon how many generators are there, and also what type of DER is connected, whether it is inverter based or synchronous based DG. So depending upon these settings have to be changed. So we have to do something adaptively. Either we have to adopt some adaptive technique which can see every time what is the network topology and what are the types of inverters which are connected in the microgrid, and then repeatedly it will keep on adapting the relay setting so that the fault can be detected. So this is a problem. This is a big challenge. So then the next problem is bidirectional fault current. So if we see the first fault, this F1 fault, then this G1 and both are feeding this fault. So this may trip. But if there is a fault here, then this is also feeding. All the fault is here, but since this generator is also feeding, and if this current IGF2 is greater than the setting of this CB2, then this will open. So this is not what was required because fault is on the main grid side. So this can operate, this should not operate. So if there is a, that is so, because right now we are using only this overcurrent relay and they have this problem because they don't have direction sense. Direction element is not there. That is why we want direction element to take care of these bidirectional fault currents. Then so you were talking about fault stripping. Right. So if we have a fault in feeder 2, then we have two generators here. One is the, since this is a grid connected mode, so grid is also there, so grid can feed the current, fault current, and also when the generator is here, so both can feed the current, fault current. So if the current, so R2 will trip, R2 will detect the fault. But what is happening if this current which is fed by this G1, if this current is greater than the threshold of this R1, then R1 will also trip. Although the fault is in feeder 2 and feeder 1 is a healthy fault, but still feeder 1 will also trip. So load connected to feeder 1 will also be disconnected because of this fault stripping of R1. So fault stripping means although fault is not there in that along that feeder, still the R1 is tripping.
If R1 is having directional element, then it will not reflect.
Yeah, yes, if so that is a good, so we need a direction. Right now we only have overcurrent. So this problem will be there when we have only the overcurrent element. If we have directional element present, then it will not trip. So it will, if directional element is there, if fault is ahead of this, only then it will trip. Otherwise it will not trip.
Right. Okay.
So this is for the overcurrent element. That is why we need the directional relay, direction element. So we need directional overcurrent relay. So we need both overcurrent plus direction current element and both. So we need these two. We will do the end operation of these two. So if current is greater than threshold and also if direction is as per the zone of relay, then it will trip. If direction is not as per the zone of that relay, it will not trip. Is it clear?
Yes, correct. It means fault stripping takes place only when one of the feeder is going under fault.
Yes.
It may affect other feeder also in case it is not having directional or the condition.
Yes.
Required. That's one.
So this will only happen if this current exceeds this threshold of R1. So
No,
it may not always happen.
Now, it may happens in case of overcurrent also,
Yes.
not faulty conditions. Suppose
In overcurrent only it will happen if this. So these two conditions need to be met. One is the
Okay.
current should be greater than the threshold which we have set in the overcurrent element. Then, if it is only overcurrent,
yeah,
if this happens, then it will also trip.
yes, now clear. Okay, go ahead, please.
Then final last issue was this blinding of protection. So, can anybody recall what is this blinding of protection?
Blind is related similar to this, na? That
How?
a relay. No, it's not similar to that. One relay will not see the fault.
Yes.
Oh,
Yes. This one.
yeah. The
So
condition is like that. One relay is unable to see the fault because
this will, if what
yeah,
happens,
yeah,
suppose if this generator is not there, so what will happen? This fault current is same as what is fed by the generator, this grid, main grid. But if it is G1 is also there, then fault current is fed by both this grid and the generator G1F. So in this case, this IGF is less than IG. So this is case when only grid without generator 1, and this is with generator 1. So when this generator is there, DER is there, the current contributed by the main grid reduces. And if it falls below the threshold value of this relay, then this relay will not see a fault, although there is a fault. So this relay is blind to the fault.
yes,
So it becomes blind. So that is the problem.
yeah,
So are all these four issues clear to everyone?
yeah, clear.
Clear, then we'll move to questions.
Yes.
So this is the first question. So a microgrid has a load of 500 MVA and power factor is 0.9 and generation of 500 plus J 300 MVA. So we have to calculate the power mismatch. So anyone, can you tell how do we calculate power mismatch? So the this power mismatch will be in which mode? Islanded mode or grid connected mode or both? And which of these modes power mismatch will be there? I think there was one question in assignment also. First question on power mismatch. No one is able to recall. Okay, then so this power mismatch will only be there in islanded mode because when grid connected in grid connected mode the load is supplied by the generator inside the microgrid as well as the main grid. So power mismatch occurs when there is an imbalance between load and generation, and this is equals to P load minus P generation. Here also it will be Q load minus Q generation. So in grid connected mode, this will be 0. Both will be 0. But in islanded mode, it may or may not be 0. It may be 0. If load and generation both are equal, then it will be 0. But otherwise it will not be 0. So in this case, will it be 0 or what will be the value of these two? So now you can calculate. Everything is given, right? This P load is given, P generation is also given, Q load, Q gen. So what will be the value for these mismatches? What will be the del P and del Q? Can you tell? This is a simple question, right?
Delta P should be 0, but I'm not sure about delta Q. It is positive or negative?
Yes,
That's my.
that we have written here. We just see this one.
Okay.
Just see this. Is reactive power of load is less or more than generation? If it is more than generation, it will be positive. If it is less than generation, it will be negative. So, what is the value here? Is it positive or negative? First, we have to calculate this. What is the load power? P and Q. Because this is MVA. This is not megawatts. So, del P will not be 0 here. Correct?
No, it's a MVA, the power factor here.
Yes. So P load will be, how much will be P load? So P load will be 500
into 0.9.
Yes, into 0.9 plus.
Okay.
That is, this is 0.9 J, how much?
So I have forgotten the concept.
Yeah, these options are given for 0.95 pairs. Let us make this 0.95. This is 0.95. And this will be 500 into sine of cos inverse 0.95. So this will be 475 plus 156. Now can you tell what will be the mismatch? This is P load and P generation is also given 500 plus J 300. Now you can easily calculate. Now what will be the mismatch? A, B, C or D?
C.
Option C, correct.
C.
So we can easily see that load is both active and reactive power are less. Load is less than generation, so mismatch is negative. Let us move to the. So this is same here which we have discussed. In islanding, load may not be equal, so there will be mismatch. This is the C answer. Now, next, this question is based upon the non-detection zone, NDZ. So here the question is, for positive active power mismatch, the superimposed negative sequence impedance is 0, positive, negative, or none of the above. So in the lectures, in second lecture of this week 5, we discussed one technique, this rate of change of superimposed negative sequence impedance. So if there is a positive power mismatch, so what will be this superimposed negative sequence impedance? Change in superimpedance. So due to islanding, will the negative sequence impedance reduce or increase? That is the question here. Any idea? You can guess. You can make a guess also. What do you think? Based upon our knowledge of active power mismatch, what will happen if there is a mismatch? How will it affect the impedance? You know that this mismatch is P load minus P jet. If this is positive, that means, what does this mean? Positive delta P. This will imply that load is more than generation. So if load is more than generation, what will happen to voltage? Will voltage remain same? Will it increase or decrease? What will happen?
Yeah, voltage will decrease.
Correct.
Load is
So
more. Yeah.
voltage will decrease. So that is why impedance will also decrease. So if we are measuring change in impedance, so this is before and this is after islanding. So this is Z2 post after islanding. So impedance after islanding has reduced. So what will happen to this change delta Z? Will
It will be negative.
correct?
Yeah, it will be negative.
This will be negative. Yes. Negative is correct. Now this is another question for this is also based on this. This is based on actually not the previous one. This one is based on NDZ, knowledge of NDZ. So which relay will operate under a high negative reactive power mismatch? What is your intuition or guess? If there is a high, so we saw in the last question we saw positive change in active power, positive active power mismatch. Here we are talking about negative reactive power mismatch. So what will happen here? Here the voltage was reducing. What will happen here if there is a negative reactive power mismatch? So if you remember that NDZ, then you can answer this question. It is directly based upon that plot between delta P and delta Q. Any idea?
It will be opposite to that. In case of
Opposite means voltage will increase. You are saying?
yeah, should be reactive power becomes more. Just like regulation, we are generating just like in power system, we are adding capacitors and all the thing to improve the power factor. So
But
we are generating reactive power. In
he,
that logic, I am telling.
here the reactive power mismatch is negative. That means after islanding, the reactive power is decreasing.
Reactive
So
power is decreasing.
voltage will increase if Q will increase, but also that thing directly relation of V to Q and F to P is that is in transmission system. Here we are talking about distribution. So this decoupling will not is not applicable here in distribution system. That is the one point. And second, this reactive power is reducing, so voltage cannot increase in this case.
Okay.
So let us see the graph then. You can easily answer if you see the graph. Now can you answer after seeing this? So this is the NDZ. Right? So this is a zone where the relay is not able to detect the islanding in this region. So the question was if there is a negative reactive power mismatch, a large or high negative power mismatch, reactive power mismatch. So which relay will operate? Which limit is going to hit? You can easily tell, right? This is delta P negative Q axis. Which relay limit is going to hit?
Frequency relays.
Which one? Under frequency, over frequency limit. This is
Over frequency.
correct. So this is a negative Q axis, right? Negative delta Q. So if we have a negative, large negative Q mismatch, then this limit is going to hit. So this over frequency relay will have to trip. For positive delta Q, this will happen. Similarly for negative delta P, and so in the last question we saw that there was a positive active power mismatch. So that is why the voltage was reducing. And
Yeah.
it goes below a limit, then under voltage relay will trip. Correct? So these are the two equations which governs this. These two equations determine this non-detection zone. So here you can see. So this since this delta Q is dependent on P and P is dependent on V also. So we cannot say that Q is directly related to F. Oh, sorry, V. And F is directly related to P. We can here it's opposite in one sense because P mismatch is causing a voltage change and Q mismatch is changing the frequency. So in one sense it is opposite is happening here. So the transmission system principles will not uh, apply in distribution system. Can you tell what is the reason of that? What is the major reason of that? Why are we not able to apply this decoupling of between P and F, real power and frequency, and reactive power and voltage? This decoupling which we use in transmission systems. Why are we not able to apply it in distribution system? What is the main reason of this? Anyone remember? Okay, I will give you a hint. It is something. It has to do something with the R by X ratio. Now you have to tell me R by X ratio is low or high in distribution system as compared to transmission system. Is it high or low? Anyone recall? How do we reach here? Because we neglect certain things. We neglect that G is 0, R is 0. We consider there is only inductance, reactance. Right? So in transmission system, this R, consider R is very less. But in distribution system, we cannot assume that. Resistance is quite large as compared to transmission. So this R by X ratio in distribution system is much larger. And as a result of that, we are not able to decouple this. This decoupling is not possible. Because of that only we cannot use our conventional Gauss Seidel or Newton Raphson load flow methods, power flow methods. Because of this, all these things change. So is it clear?
Yes.
Let us move to the next question then. So our correct answer is over frequency relay. So this is very easy question. This is very simple. Minimal power mismatch necessary for rate of change of frequency islanding scheme to function is. This is direct fact. 5, 10, 15, 20. What is the answer? This is the answer, 15%. So when we were discussing about the different techniques, passive, active, hybrid, and communication, we saw that one of the major demerit of these passive techniques is the design of threshold, and also they need a minimum threshold to operate. If there is a zero mismatch, then these techniques fail to operate because there will not be any change in voltage, frequency, or other parameters that we measure. Because this will only change when there is a change in either delta P or delta Q. So this is the minimum threshold we require. Then the next question is, this is also a simple question. In the this also we have discussed while we were discussing the block diagrams for all the techniques. So is the rate of change of phase angle detection scheme the estimated rate of change of phase angle deviation in case of islanding is greater than threshold, less than threshold, equal or there is no change. We saw this plot diagram with parameter threshold. This you have to fill. If if it is satisfied, then there is islanding. If not satisfied, then no islanding. Here we measure the parameters. So what is this? Is it greater, less than, equals to? Which one is correct? We have already discussed this.
It should be greater than.
Correct. Should be greater. So all because we discussed in the last question also that we need a minimum threshold. When we're talking about a minimal threshold, then it has to be greater than. So if it is less than, it will never happen. So whatever we are measuring, these measured parameters, they should be greater than the threshold always for all the passive technologies, all the passive techniques, even in the active or hybrid that we use. In all these techniques, we check this. So it should be always greater than the threshold. This is next question. The expression for rate of change of superimposed negative sequence impedance. Which one is the correct? So here we are talking about dz2 by dt, which is, so this is in continuous domain, continuous time domain. What you see here, which domain is it? Is it time domain? So here we have t also, k also. T is time, but why we have k here? So this signifies something. So in the fourth week we have discussed these different phasor estimation techniques. Do you remember any phasor estimation technique? This is our voltage signal or current. This is a continuous time domain signal. what will happen if I sample it? So we'll get something like this. Let us take 4, 5, 6, 7, 8 samples. So here we have n is equals to 8. So 8 samples per cycle. So in phasor estimation techniques, what are we doing? We are estimating the phasor. So V or I phasor. Here this is voltage, so and we only have these samples. From these 8 samples, we have to reconstruct this original VT. We don't have this red curve. The processor only has these blue dots, samples for each cycle. So if this is a 50 Hz signal and number of samples are 8, so frequency of signal is this. So what will be the sampling frequency based upon the number of samples? Can you tell? Anyone? We are talking about this samples only. So this is at T1. Suppose if this is Fs and it is Ts. Time period is sampling time time period is Ts. So this will be 2 Ts, 3 Ts. So this T is replaced by NTS here. Or we can say here we have taken K, so this is KTS. And so in between these two we have only this. So time at K minus 1 and time at K. Difference between these two samples is this. So we can have different phasor estimation techniques. We discussed DFT, in that we discussed half cycle, full cycle. Then we discussed also the least square phasor estimation, cosine transform also. So after we do this phasor estimation, we will get these phasor of voltage and current for all the three phases. So we will have VA, VB, VC, IA, IB and IC. So from these voltage VA, VB, VC and IA, IB, IC, can you calculate the negative sequence impedance? What will be the value of this negative sequence impedance? So for doing this, measuring this, we need this. We want rate of change of superimposed negative sequence impedance. So to measure the rate of change, we first need this negative sequence impedance. So how are we going to calculate the negative sequence impedance? Can you tell? Anybody recalls that? From the actual voltage signal, we had the samples. From samples, we have obtained these phasors VA, VB, VC. Now the next step is to find this negative sequence impedance. So how do you find normal impedance? What is Z? Formula for Z. How do you find impedance? This is simple, right? Impedance is voltage by current. So this negative sequence impedance is negative sequence voltage by negative sequence current. But we only have this VA, VB, VC. From here, ABC, I want to go to V012 or V120. Right, Ali? So this is sequence domain. This is phase domain. So phase values, you want sequence values. So you have the matrix, transformation matrix in between. If you multiply the phase quantities VA, VB, VC and this current IA, IB, IC by using this transformation matrix, you can find out the positive sequence, negative sequence voltage. This transformation matrix into VABC. Similarly, current also. If we simply want this, we can directly multiply it with one row of this. So now from this we have both negative sequence voltage and negative sequence current. If we have both, we can find out the negative sequence impedance. Okay, so we have reached up to this point. We have calculated the negative sequence impedance for one sample. But I want to calculate the rate of change. So we want to know delta Z by delta T. So how am I going to calculate this? Z2 T plus 1 minus or plus. Okay, here it simple. We're talking about samples. So what will be this? Plus or minus? That you have to tell. This is the final step. Now you have to tell whether this is plus or minus. Which one is correct? Everything is given. What should be the correct answer? Anyone? Is C option correct?
Yes.
C option? Yes. This will be the correct answer. B. For kth sample, we have k minus 1 sample. We don't have this k plus 1 sample. So we don't know this. For we have k minus 1 sample, so what we can do? So this is k and this is k minus 1. This is tk minus 1. So we have to subtract the current negative sequence impedance from the previous one, current time instant from the previous one, and we will get this rate of change. So this B option is correct. Is it clear? Is there any doubt? Priyanka, is it clear?
Yes, sir.
Okay. So let us move to the next question then. So the limitation of conventional islanding detection techniques is or quality degradation, complex structure, result in and detection zone, or all of the above. Which one is the correct answer?
C option.
Only C?
Should be all of them.
Yes, because we saw in so these conventional techniques are these passive techniques, and in passive techniques,
Yeah, D option.
so this conventional are passive plus some active also. In passive technique, there is no power quality degradation. Is it clear or there is a confusion? If this question would have been limitation of conventional passive islanding detection techniques, the answer would have been this. Because in passive techniques there is no power quality degradation. Correct? So
Yes.
this question is as per the lecture which was mentioned in the lecture. So there the conventional techniques include this. They talk about both these the earlier versions of this active and passive. So that is the answer is all of the above. Otherwise the answer would be this. Only C. And the next question is in signal injection based islanding technique, injected disturbance signal is what type of signal can we inject at the PCC? So here we are injecting some disturbance. What kind of disturbances can we inject? Low frequency, negative sequence, component, pulse signal, or all of the above. So here we can inject all of these, any of these, depending upon the technique which we are using. So all of these can be used. This also we have discussed, so this should be easy to answer. In feedback-based islanding techniques, in case of islanding, DER operates in which region? And this is also the demerit of this feedback-based islanding detection techniques. So DER operates in stable, unstable region, or it is not affected. Even we just discussed this in the beginning of this session. So DER will operate in the unstable region, and that is why this is a demerit of this method. So do you have any doubts in the week 5 material? Any specific doubt? If you have, you can ask. We have 40 minutes. Otherwise, we can move to the next questions. So no doubt, is everything clear? So then, so tell me, so then why is this feedback based islanding technique driving the DER into unstable region? If everything is clear, can you answer this? So we are saying that these techniques, they drive the DER into unstable region. Why? Because this is a positive feedback. In control theory, we study two types of feedback. One is positive and one is negative. So in oscillators, we use this positive feedback. Here also we are using because we want to inject a disturbance. Our aim is to make it unstable. But if in negative feedback we use when we want to control something, in amplifiers or oscillators we use this. But when in PID, all these controllers, when we use the negative feedback. Because we want to if we give some input, we want the system to stabilize. But in oscillator amplifier, it will not happen. But since this positive feedback that we are injecting, this magnitude is very small. So this is not able to drive the DER to a very unstable region. Slight instability is there, not much. That is why this is a disadvantage of this technique. Then let us move to the next question. In which mode of operation the fault current in microgrid is high? So grid connected mode, islanding mode, or both? Which will be the correct option? This is the first grid connected mode, this is islanded mode. So here there are two currents. One is from main grid and one from this DG. And here we have only one current from the solar PV. And that too is limited to 2.02 per unit. So now can you answer this question? So in which mode of operation the current is high?
Would be grid connected mode, but yeah,
Yes. Because
here is a limiting factor, no? By
correct. So correct answer is the grid connected mode. So in grid connected mode the current is high. This also we discussed that due to bidirectional faults, which type of traditional relays are unable to provide safety protection? Distance relay, unidirectional overcurrent, instantaneous overcurrent, or all of the above. Can you answer?
should be unidirectional overcurrent relay, because scatter is in only one direction.
Correct. Because we want bidirectional for current protection. So unidirectional overcurrent relay will only provide protection against one direction of current. Do you know where do we use this distance relay? Are we using it in microgrids?
No, mostly these are used in transmission lines, long transmission lines. Mostly distance relays.
We are using this distance relay in transmission line for line protection, line for fault detect for localization and fault detection. And this in distribution system mostly we are using this overcurrent relay. And that too these are unidirectional. And as the penetration of DR increases, the bidirectional currents will increase and we will have to go to directional overcurrent. So let us see the next question. This is correct answer. This is a good question. So if you have understood these techniques, then you will be able to answer this question. So a disturbance current of this value ID is being injected into the D-axis current controller. After islanding the frequencies present in the PCC voltage R. This is a signal injection based technique. And we are injecting this disturbance into the D-axis current. There's some delta ID we are adding. There is some IQ also, IQ current. So from I, A, B, C, we have this phase currents. From here, we go to this DQ frame, ID and IQ. We buy some unsuitable transformation matrix. Now what we are doing, we are injecting the disturbance in ID and we want to see what will be the, for PCC voltage we will have to see current also there. From current we can find voltage also. If we apply the C inverse we will get this IA, IB, IC. So in this current you will find the frequency components different. So omega naught is already there. This is the fundamental component. And we are adding some disturbance also. So because of disturbance, what will happen? There will be a fundamental component plus there will be some components which will be because of this disturbance. Because we are injecting a disturbance, this should not be omega naught. I'm sorry. This is not omega naught. This should be omega only. This is omega d only. But the fundamental component is omega naught in the current. And this is the disturbance frequency omega d. So in the fundamental, if there will be change in frequency, so this will not be correct, right? Because it is showing that there is only one component which is disturbance. But there will be fundamental will be the main component because disturbance is the magnitude is very small. So fundamental will still dominate. So fundamental component will be there, plus there will be some other frequency components. So what are those frequency components we have to check? B, C or D. So what do you think? B, C or D? So apart from fundamental, there are two more components. One is omega naught So one is omega naught plus omega d, and one is omega naught minus omega d. So if we use this transformation matrix, we will find these components in the current as well as the voltage. Is there any doubt? Jay, is this clear?
Yes, it's clear, but
Yes, but
I'm forgetting some expressions. That's why I'm not speaking. So please conclude. Yeah.
no problem. The expression is difficult to remember, but what we can remember is that these frequency components will be there whenever we inject a disturbance. Because when you will this transformation matrix that we have here is C, it has cos and sine components. So because of that, you will have this cos plus cos, sine plus sine terms. When you will combine these, you will get this omega naught plus omega d and omega naught minus d terms. That is why we are getting these components. Because of this cos and sine components which is inside this matrix, transformation matrix. It is something like cos theta. Theta comes from the phase law group. So these things will come later also. So that is why I am not going into detail. Then similarly we have this sine terms like this. Here are some, I think half, I don't know exactly. It is half. I have to check this. But there are such components are there, such sine and cos components. So if you multiply this ID and IQ, then you are saying this will multiply, this will multiply. In ID term we already have a cos here. So cos when it will multiply with this theta, then it will be cos A, cos B something. So you will get something cos A plus B, cos A minus B. These terms you will get. That is why we are getting this omega naught plus d and omega naught minus d components. This is all because of this transformation that we are doing from ABC to DQ field. When we will study this grid forming converters, I think there we will discuss on this again. There it will be clear, these transformations. So let us go to the next question. So which of the following relays are used for the protection of distribution network in the presence of DER? This we have already discussed. I think this third time we are discussing this concept. Overcurrent, directional overcurrent or distance.
Directional overcurrent relays.
Correct, because we saw that which you asked one question, right? Which one?
Yeah.
For that blinding protection, right?
Yeah.
we have a fault here, that we have a generator here. So what will happen? Will not here. So if there is a fault, this generator is feeding. If this generator is also feeding, both are feeding. This is relay R1, this is relay R2. So this is the faulty feeder, and this is the healthy feeder. This generator is also feeding here. If this relay is saying this current, suppose IG1, this is IG2 is I small g, this is capital G. So this relay is saying IG current, and this relay R2 is saying IG plus IG, which is also fault current IF. If this IG current is more than the threshold value of this relay R1, then R1 is also going to true. All the fault is there in the fault this feeder 2, not in feeder 1. This is happening because this is a simple overcurrent relay. It does not have any direction sense. But if R1 is designed with the direction element also, so direction plus overcurrent, then R1 is designed, then R1 will be designated for faults which happen after this relay. Similarly, R2 will be designed for faults which happen after here. So if there is a fault F here, R1 will not trip. So we need a directional element. So directional element overcurrent relay will help us. Then this is the next question. This is also based upon the directional relay. So we have to select the correct pair of polarizing and operating quantity for a directional relay. So which option is correct? So which one is the polarizing quantity and which one is the operating quantity? Can you tell what is the principle of a directional relay? How is it able to distinguish between the forward and backward faults? Any idea? You said that you have no doubt in the material. Or the question is very simple, it's too simple. For this distinction, what we do is we measure the phase. Measure the phase difference between voltage and current. This is the voltage and this is current. So you will measure the two before and after the fault. Then you have to check what are these phase angles. So this phase angle will change because when the fault happens, the impedance seen by the seen at the fault point, it changes. So the fault path is when the fault happens, what will happen? The current will increase and voltage will decrease. It will reduce. There will be voltage dip and current will shoot up. But the phase difference of change in phase of voltage is not much. Voltage phase, voltage, this is a phasor. So it has a magnitude and a phase. So this phase it does not change much. That is why we take voltage as a polarizing quantity. Because although its magnitude may change, but since the directional relay is operating based upon phase, so we are more concerned about phase. So we need to have one reference. So this is a pre and post. So polarizing quantity is the reference quantity, we can say. So if the pre and post both are different, then the reference will change and will not be able to correctly measure the difference. So when the fault happens, the phase angle of voltage does not change much. So we take voltage as polarizing quantity, but the phase angle of current will change because now the impedance path has changed. So the impedance seen at this point will change. Impedance of this is different, this is different. And that will determine the phase of current. And depending upon, suppose the relay is here, so whether the fault is here or here, that will determine the impedance, the path of fault path impedance, and that will also decide the current phasor. So based upon this phasor, whether it is less than 180 or more than 180, we can say whether the fault is forward or backward. So now can you tell which option is correct? Which one is the polarizing quantity and which one is the operating quantity? Jay, can you answer?
Not very sure. So I'm not answering.
Okay, we are discussing that voltage is a polarizing quantity because we want a reference and voltage during fall the voltage phase is not changing.
Yes, yes.
So voltage
So
is the polarizing quantity. So which option is correct? Polarizing quantity is this PQ. So this option is correct. Because voltage is the polarizing quantity. And current we are taking as the operating quantity. Because we are taking phase between voltage and current. I will just repeat it again. Because this is an important concept for direction relay, which is the backbone of this new distribution of for the distribution system in presence of these DERs. So if the direction relay works on the basis of this, on basis of determination of this phase angle between the voltage and current. So whenever we measure a phase, we should have one reference. When we make this phasor diagram also we take something as reference, right? So if we are taking this phasor as a reference, with respect to this phasor we will draw everything. Right? Suppose these are the two buses. This is VS, this is VR, so we are taking VR as a reference. And suppose this is R plus JX. So this is R plus JX into I, and this becomes VS. So this becomes the angle. So this is because we have taken VR as a reference at angle 0. So with respect to VR, VS is leading by an angle theta. So we are able to know this angle of this theta. Similarly, when we want to know the phase difference between voltage and current, we take something as a reference. So we are taking voltage as a reference. And why are we taking voltage as a reference? Because during the fault condition, the voltage phase does not change much. So we exploit that fact. So this V pre angle of V pre is almost equal to angle of V post. But the I angle of I pre is not equal to I post. That we have to calculate. So since we have this reference, we know and we can calculate this difference. So by measuring this difference, we can know depending upon how much is this phase. And we can distinguish between forward and backward fault based upon this angle. That is the main basic principle of direction relay. So here this voltage becomes the polarizing quantity and current becomes the operating quantity. Or it is also called actuating quantity. Is it clear, Jay? Is this clear now?
yes, it's now clear.
Good.
Clear. Yes. Yes.
Good.
Sometimes your voice is giving echo.
Mhm.
Maybe you may be sitting in a big hall, or your
Okay.
mouthpiece is not near to your. Maybe
Now,
sometimes.
is it okay
Yeah.
now?
No, it's okay now.
Sorry for that. Actually, I am also having little cold, so that is why my voice is not good today.
No, sometimes happens. Not always.
Okay, so this we have already discussed. So questions are done. So did you do the assignment? Assignment 5?
Yes.
So do you have any doubt in that?
No, now clear. Lot of doubt was there, but today got cleared. Many of doubt got cleared. Now good.
If you have any other specific doubts, you can ask. We still have 5 minutes left.
No, I have to go through it again. The lecture material.
You can ask in other next week also. You can ask
Yeah.
if you have any doubt.
It was the most
Yes.
complicated lesson.
Yes, it was little bit difficult. So
Yeah.
you can watch the lectures again, and still, if you have doubt, you can ask. And if you have any doubts in the previous week, up to week 4, you can ask.
So, fourth week it was not so much hard to understand. A lot of calculation, lot of concept was in this. So really needs attention.
Yes.
Every time. I'll ask in next time. Let me go once again through lectures.
So did you understand? Did you
Yeah.
understand this difference between these 4 detection techniques? These 4 techniques: passive, active, hybrid, and communication.
Yeah. That is.
This was the basic, the main theme of the entire week. So if you are able to understand this, then you will be able to understand other. Once again, if you go through lecture, you will be able to understand. The next lecture also, next week material is also a little bit based upon this also. It's little bit complicated.
Yes, sir. You know what?
Sorry, I could not hear it.
Yes, I will go through it.
Definitely, you can ask anytime. In any subsequent weeks also you can ask. I didn't discuss the assignment question. Do you want me to discuss the assignment questions also?
No. Lot of things are clear now. So okay, we can close.
Okay, so for others, do you have any doubt? Rupesh and Sangat, Anusha, do you have any doubt in week 5 material? Jay, is this way of conduction of this live session okay, or
That's okay.
change something?
No. You are giving lot of time to interact with. So no. Say okay. Your pace is okay. Not too fast, not too slow. It's okay. A lot of the chapter. This chapter was little bit complicated. So lot of you can understand. Lot of concept, lot of derivations and all. That's why.
Now, subsequent weeks will become complicated. The initial were the basic. Now you will have to spend more time, give little more time and attention. But the concepts are not that difficult. The main thing is they require little time. We go through them again and again, we will be able to grasp.
Yeah.
Thank you for your feedback.
Yeah. Thank you. See you.
If you have any doubt, you can ask in any of the subsequent weeks.
No, I'll definitely. I'll ask.
So shall we close then?
Yeah, we should close.
Okay.
Nice. Very nice to hear you. Thanks.
Thank you, Jena. Thank you. Thank you, Rupesh. So thank you everyone for joining. If there are no doubts, we can close the session. Is it okay, Rupesh? Can you hear him? Okay, then let us meet. Yes.
Yes, let us close now.
Yes. So let us meet next week, same time,
Yeah. Thanks.
Tuesday 6. Okay. Thank you, everyone.
Yeah, thanks.
This generator is.